Hi, I'm Diane, and today we're going to do an example of a two-proportion z-test. A company claims their new product will reduce the number of defects in their manufacturing process. To test this claim, a sample of 100 units was randomly selected from the production line before the introduction of the new product, and another sample of 100 units was randomly selected after the new product was introduced. The number of defects in each sample was recorded, and the results are as follows. Sample before, 15 defects out of 100 units. Sample after, 8 defects out of 100 units. We want to test whether the proportion of defects has decreased after the introduction of the new product. Use a significance level of alpha equals 0.05. And so here are the different inputs we need. The number of successes for the before sample is 15, and the number of units is 100. Successes after the new product was introduced is 8, and the sample size is also 100, and the alpha level is 0.05. So the first thing we need to do is state the parameter of interest, which is P1 minus P2 is the true difference in proportions, old product minus new product, of defects. The procedure, two-proportion z-test, and the hypotheses are written as follows. The null hypothesis, the difference in proportions is 0. The alternate, the difference in proportions is greater than 0, because if the proportion was greater before the introduction than after, then when you subtract them in this order, the difference should be greater than 0. The plan. So first we check the conditions. Random, and it's stated in the problem that there's a random sample of 100 units before the new product and a random sample of 100 units after the new product is introduced. Large counts. First, we have to calculate p hat combined. And that is, for the numerator, it's the sum of the successes for both samples divided by the sum of the sample sizes. So that's 15 plus 8 over 100 plus 100, which is 0.115. And then we use the p hat combined when we do the large counts condition check. So we're going to multiply each of the sample sizes, N1 and N2, which happen to be the same, by p hat combined and by 1 minus p hat combined. And we see that we get 11.5, 88.5, and then for the second sample, it's the same numbers because the sample size is the same. Since these are all greater than 10, we say it is safe to use Z procedures. The third condition is checking independence, and we need to make sure that our populations are at least our sample size times 10. So let's see, we don't know the exact population size, but this is a production process. And so we say it's safe to assume that there are more than 1,000 units in the production process before the new product and 1,000 units after the introduction of the new product. The do part, we look at the test statistic, which is the difference in the p hats. So p hat 1 minus p hat 2. We calculate those p hats and we get 0.15 and 0.08. They're each the ratio of their number of successes to the sample sizes. And then our Z statistic is p hat 1 minus p hat 2 minus the difference under H naught. And under H naught, we've said the difference in proportions is 0. So we're just subtracting off 0. And then the denominator is the square root of p hat combined times 1 minus p hat combined over N1 plus p hat combined times 1 minus p hat combined over N2. And we get 1.5515. And I wanted to make a note that this denominator can also be written as it is down here in the lower right corner, that those two are equal to each other, as sometimes you see it both ways. Okay, so we've got our Z statistic of 1.515. That is going to define our p-value. So we're going to figure out the area that's more extreme than our test statistic of 1.5515. And we can also figure out our Z critical value. So the critical value is the z such that the area to the right of z, because it's a right-tailed test, is it has an area of 0.05 to the right. Okay, and this critical value then defines the rejection region for the right-tailed test. So anything to the right of 1.645, so greater than 1.645, we will say that we're going to reject H naught. So right off the bat here, we can see that our z statistic is not greater than 1.645, so we're going to fail to reject. And so that's one way of looking at it. Another way of looking at it is to calculate the p-value. So as I said, it's the area that's more extreme than 1.5515. So we can use in the TI-84 the normal CDF, where we tell it the lower is 1.5515, the upper is just a large positive number. I use 10,000. The mean is 0 and standard deviation is 1 because this is a z. That's the definition. And we get 0.0604. So you can look at it either way. You can either say, well, the p-value is greater than our alpha of 0.05, so we'll fail to reject because of that. We do not have convincing evidence that the difference in defect rates before minus after introduction of new product is greater than 0. In other words, we do not have convincing evidence that the new product reduces the defect rate. And so you have the same conclusion whether you compare the critical value to the z statistic or the p-value to alpha. Okay, thank you for listening.